Cool. So I was going to say good morning, but it's not morning. It's not even morning in my time zone. But I certainly feel like it's morning. I watched a very interesting video by a public speaker who comes from Ireland. Actually, I'm from Ireland as well. And he said that the way to engage an audience in what you're talking about is to tell them a story. And so my whole story is I arrived, I flew out from Dublin, but the flight was delayed 3 times. And I got into O'Hare, and I had specifically tried to avoid flying on the 737 MAX 800. And because I was delayed, I then had to fly on the 737 MAX 800. And the rain was pelting down. Obviously, we didn't crash, but that set me up for this. Then I didn't have time to practice my speech or anything like that. So I'm literally completely winging it at this point. So I might ask you questions to fill in for all of the various gaps I have and what I'm going to talk about. So, who cares about secure boot? I care about we all. Let's hope we all care about secure boot. And if you don't care about secure boot, don't stay around and listen to this. So, what I'm going to say is we have a convergence of cloud management services, AWS, Microsoft, ARM. I have somebody else down here, IBM. IBM is a good one. But from the perspective of secure boot, you have fragmentation that looks a lot like the fragmentation we see in the low-end embedded space in just about everything. And I've been working on a project with ARM called mbed Linux, which is based around this fantastic cloud service here that both ARM and Intel are participating in called Pelion. So we have the cloud side of it kind of sorted out. We know how we want to talk to the devices and how we want to update them. And there's a nice correlation to the lower-end mbed stuff, hence mbed Linux. But when it comes to secure boot, I think what we found was kind of a vast array of differentiation, which wasn't great. So initially, we started out on a vendor solution, NXP solution. It was perfectly fine. It's a thing called HAB, High Assurance Boot, and HAB will do everything that you wanted to do. But it's specific to NXP. So if we wanted to go to TI or we wanted to go to Qualcomm, we would have to use their vendor solution again. So what we settled on was a thing called Trusted Boot, being good ARM citizens. And Trusted Boot is pretty simple. It's defined as a series of boot stages, BL1 being your boot RAM, moving on to BL2, which is your first piece of code that you can, first piece of rewritable code, moving on to BL3, which is like your grub or your other stuff, whatever else you want to run if it's not grub. Uboot, in our case, was what we were running. But interestingly enough, ATF doesn't mandate any particular secure boot steps past its own bit. So ATF tells you, well, thou shalt verify BL2 in a specific way, and thou shalt verify BL3 in a specific way. It's via a thing called the FIT, which is a firmware information package. If you work in this industry long enough, or even a very short time, your head will become filled with a whole bunch of acronyms, TLAs, 3-level acronyms, or in the case of Intel, ETLAs. A little bit of an x86 joke there. So UEFI Secure Boot is a standard way of doing secure boot on x86. Originally, I think Intel did that on EDK2. I'm mostly sure Tiano Core supports the same level. I'd be happy to be told otherwise if that is not the case. I think EDK2 and Tiano Core are interchangeable for the purposes of secure boot. They're the same project. I did not know that. I thought they were separate projects. No. Okay. So with secure boot, you can sign the next thing that you run after your BL3 in our case. I've been told actually you cannot sign arbitrary bits of binary, so you can't sign an init ramfs or a boot script. And UEFI has a well-defined set of key types, which in comparison to what we were talking about here on the ATF way of doing it, these keys are, for example, burned into your sock, typically an OTP key, whereas in UEFI you have this kind of very interesting concept of a platform key, which is a vendor key. Your Microsoft or your Dell can provision that into the device. A key exchange key, which is then used to verify your database, which is a set of allowed signatures. But on x86, you can take full control of these keys, which of course is really not what we want to do on an embedded ARM system. You know, typically, you would want to have that locked down, and you would not want people who had physical access to your system to be able to just arbitrarily replace keys for obvious reasons. So that's a way that the UEFI and the ARM TBB are different. Conceptually, of course, on ARM, you probably would lock those keys down. You wouldn't allow people to have who have physical access to the board to just update the keys.
I was just saying the ability to change the platform key on UEFI is based on whether or not you can disable secure boot. So if your platform doesn't allow you to disable, if you can't disable secure boot, you can't change the platform key.
I think that's logically consistent. Yeah, that makes sense to me. I'm not sure if the standard mandates whether or not you should be able to replace those keys. I'm pretty sure it doesn't.
There's probably a debate around it.
Yes, Grant's right. So I'd like to cover Uboot FIT images here as well. So far, if we can cast our minds back to the ARM way of doing it, we have our BL1, BL2, and BL3. And BL3 in this case is Uboot. For the purposes of our discussion, we'll say it's Uboot. And like I said previously, at that stage, you're done. The spec doesn't mandate that you do your secure boot in any specific way past that point. But Uboot has this thing called FIT images, and FIT images allow you to do exactly that. So if you've established a root of trust, a chain of trust, from your boot RAM all the way up to your runtime Uboot, you still need to have subsequent steps. It's not just good enough to get to Uboot and then run some random kernel that some hacker rewrote on your flash, clearly. So Uboot is the FIT image is basically an archive that has a bunch of descriptors with some SHAs and some key material that allows you to verify the contents of that archive. It works pretty much as you would expect it to work. But what it doesn't do, from the perspective of making a full and complete system, is it doesn't really, and nor should it, it doesn't give you a way to update your firmware. It doesn't speak to that at all. It's a verification. It's a next step verification, and in that it is simple and it does it well. There's absolutely nothing wrong with FIT images, except, let's compare to UEFI. Right, so let's go back here to this concept that I kind of glossed over of the the database and the excluded database. So this mechanism here gives you a way to revoke keys, and that's pretty important actually. You want to be able to revoke a key in the field, and Uboot FIT doesn't really fit that model too well. You can't really revoke a key in a FIT image. You must replace that FIT image. So there's kind of a difference there conceptually in what they do and what they implement. And in that, I think the UEFI spec is more powerful, if more difficult to get to grips with, particularly on ARM, because for our model here, for the model that I'm describing here, where we use Uboot, which, let's face it, for the majority of ARM systems will be the way it is. You will get to Uboot at some point. You won't be getting into grub, and you most likely won't have an EDK2 based firmware, nor do you want to mandate that, nor do you want to go and write your own. Write your own EDK2 for a fully functioning board is a big undertaking. But what might be kind of interesting is to add UEFI secure boot services to Uboot and other pieces of collateral that go with that. And by collateral, I mean obviously OPTI. So for the uninitiated, of which I'm probably one, we have boot time services and runtime services. So a boot time service is a self-explanatory thing. It's there for as long as you're booting. And at a certain point in the boot process, you call this guy here exit boot services. And that disjuncts all of the previous code that tells the kernel to get rid of it and no longer have it in the map. And it makes a call into the firmware, and the firmware can do firmware-specific things to switch off services and maps and so on associated with boot time services. After that, you have runtime services. So the only runtime service I know much about is Capsule Update. I think there are other services, probably to do with timers and watchdogs. I'm not particularly familiar with those. So that, like a few boot time services, when you're booting up, you can call back into your firmware and have it print stuff out for you. It's very, very simple. But the runtime services. So the runtime service I care about mostly from the perspective of implementing secure boot is Capsule Update, actually. And Capsule Update, why do I care about Capsule Update? I care about Capsule Update because if you think about it, they have a Pelion service that's downloaded stuff to 10 different boards of 10 different vendors. But how do you update the flash? And where is the flash? And who owns the flash? Is it NAND? Is it NOR? Do I need to have a script on every single board that understands which board it's running on and how to update the flash and any quirks that go with it? Whereas if you can make a UEFI call to a runtime service using a nice defined, well-understood callback like Capsule Update or Update Capsule, I always get it wrong. But which one is it, Capsule Update or Update Capsule? Nobody can remember. Well, we know what it does. So it tells the runtime service to take a capsule. If there's a flag in that capsule that tells the system whether or not it needs to reboot to update or whether it can go on the runtime, everybody reboots, to my knowledge. And the other great thing about Capsule Update is the keys that you previously used, your DB and DBX keys, are then reused to verify your capsule. So the firmware knows how to update itself. The keys you can manage via the Capsule Update method. And all the code just works. No, I'm kidding. None of the code is in place for that at the moment. So if I were to go through just my own feelings on it, I don't talk about my feelings much, I've been told by various people in my life. But my own feeling on it is, actually, it's the right way to go for that reason. because actually having a whole bunch of different ways to update different boards is an incredibly bad way to do it. Having a set of keys that you can revoke and update is a great way to do it. It's very important for people delivering secure boot systems, and Lunaro is working on all of this stuff right now. The implementation details of that are way more than I can go into, and I'm not entirely looped into every single bit of it. But my understanding is Uboot will provide at least the boot time services for Capsule update, probably the runtime services eventually. Some of that will be done inside of Opti, maybe not. Again, you would have to ask Ilias, who was in here previously, to give you details on that. But I think this is a space to watch, and there's a lot of work still to be done and a lot of fun to be had doing it. And I have a whole other slide here. I choose UEFI if Uboot FIT is just as good, but the answer is Uboot FIT is not just as good. So we go past this. And here's a matrix of what I would like to do if I had more time on the project that I've been working on. Let's see if I can get rid of this thing here, which I don't. So here's the way we do it right now. BL1, BL2, FIP image, Opti, Uboot. Opti does, sets up trust zone and the secure enclave. Uboot parses the FIT, validates the kernel, the init.rd, boot script. Boot script describes various simple bits to boot the system up, as a boot script should. Linux gets booted by bootm or bootzz, and we have a board-specific update path, which doesn't, that sucks, really, as a system design. Anything that's board-specific sucks. If we were to introduce UEFI Secure Boot into this, so this is an existing system. And in an existing system, you don't want to have to say, oh, I'm going to replace ATF right now with Tiano Core. That's a huge amount of work. And you know, if vendors are shipping like this and ARM is mandating this, we should stay on this path. So the least impactful way from a work point of view is to add UEFI Secure Boot into Uboot. And of course, Uboot already supports boot EFI. You can run SUSE on a Raspberry Pi 3, for example, and it does boot UEFI when it does that. I've been told by Ilias that these two bits here on my slide are incorrect. You cannot sign arbitrary elements. You can just sign and validate the next thing that you're going to boot after your UEFI firmware. So at this stage, actually, Uboot would be the UEFI firmware. So it's not really a UEFI firmware, but it doesn't matter because it will implement the boot time and runtime services to support it. And what you get is the key database that you can update, and you get a standard way of updating your system then via Capsule. And I think that would be it's not exactly right. It hasn't actually been implemented. But if I had another year on my project to implement it, I would do something like that. Or I would try to take in code to do something quite like that. Yeah, I see a hand.
Quick question. So on your perfect world after thing, would Uboot, instead of it doing a secure boot sign, because it cannot do the kernel, the init.rd, and the boot script, would you instead have it do a signed grub, and then grub would load a signed kernel, init.rd, and boot script?
Well, me, I would not do it that way.
Right.
Oh, so what I think you would do here is Uboot FIT.
Okay.
That's a good question, because we've got the same problem, and FIT was primarily designed to solve the packaging things up problem rather than the actual signing problem. And with the edge platforms or that kind of deployment, even if you're not talking edge, when you're talking about AB operating system deployment where you need to be able to, it's out in the field, it needs to be reliable. If the update fails, you want to fall back and you might want to have an update image. But that kind of scenario, you've got several things that need to be packaged together and you probably want it all signed. It could be done simply with the kernel image and just package up the initRD with it and have the boot stub, so sign the whole thing, and Uboot will verify it and then go and run the EFI stub, boot the kernel, and off you go. So we could actually build that into the Linux kernel proper. True. Another way to do it would be to have, mainline Linux uses stub. We could do a stub but all of those are basically the same thing. Sorry, that's not entirely true. If you got all packaged up as one, you would just verify one thing. If they're separate pieces, we do something like stub. And so the next step goes, right, the contract is you will boot me, and I will make sure that the next things I boot are signed.
So what's the embedded Linux? So actually, previously it said embedded is for the embedded IoT. But if we switch the circuit board into the UEFI-based circuit board, so what's the target market? It will be for desktop or PC?
Well, okay, so that's a great question. The title of my slide right here is mbed Linux, right? So in this case, we're talking about it runs on Raspberry Pi 3, runs on the NXP Pico 6, Pico 7, the AMX8 Mini. Am I forgetting a board? But that class of embedded Linux board.
Yeah, it's still
laptops.
embedded. It's still embedded, but switching to UEFI simplifies a bunch of development, and it simplifies a bunch of management, right? So we're still doing it better, and you can still do vertically integrated stacks. But by going this way, it enables device management by an OS vendor, which means it's easier to keep things up to date because you've got more engineering around that.
So do you have a web link for the embedded Linux source code?
I do, but I haven't written it down because I suck. But here's one I made earlier. I can't escape from this. How many Linux engineers does it take to escape from a slide? At least one. Here we go. Let me show you the web page.
So do you have the special ATF version requirement? So I saw in your slides that the ATF web link is pointed to the Chromium Git repository, but not the trustedfirmware.org. So trusted firmware is the latest ATF version. So I saw your web link is pointed to the Google Doc.
So these are references right here. These are references. I suspect I'm going to get kicked out of this room.
Yeah. You use the Google source.
Oh, this. So
yeah.
This is just the first hit in Google. But what I will do is...
For the latest ATF, it should be pointed to the trustedfirmware.org.
Yes.
Okay.
Yeah. So what I will do is I will put some extra links into the shed for this, pointing back to mbed Linux. I see I have one more question here, so I'm going to let you speak, and they can take us both on. Okay.
So what about those boot script which you specified in Uboot flatted image tree, right? So why does boot script even need to be part of an FIT when it can be a part of initRD?
It's all Grant's fault. No, it doesn't. It doesn't. That's just the way we did it in our system.
Okay.
And I just gave that example, but you are not required to have a boot script in there.
Okay. Right.
Okay, we're done.